Hey team, in this video we are now talking about fluid that is moving, that is flowing. We're going to understand what causes fluid to flow at the fundamental idea or the fundamental level and learn an equation known as the continuity equation, okay? First, let's recognize very briefly in all the other prior videos we learned about the pressure in a liquid or at the bottom of a fluid. We learned about how we can displace liquids, and there's a way to find volume based on that. We learned about something known as the buoyant force. We learned Archimedes' principle, describing what causes things to either float or sink. All those examples, the water or the fluid, okay, whether it was a liquid or gas, remember both of those are fluids, it was stagnant. The fluid was staying still. Now we're changing gears, okay? We're going to look at what causes fluid to flow in the first place, and then we're going to learn over the next few videos, okay, some of the underlying physics behind that. So I have some 3 examples here showing ideas or examples of fluids flowing, whether it's water flowing down a stream, water coming out of a hose, even like vapor or gas. Gas is also a fluid. The physics equations we're learning now applies just as evenly to liquids as it does to gases. One thing to keep in mind, team, remember, we're zooming in, or if we zoom in, when we're talking about fluids, fundamentally, we're dealing with little particles that are all moving or that are all together, maybe bumping and colliding into each other. And that's tough. That's weird because all the other topics in this class, for the most part, are dealing with 1, maybe 2 rigid objects. And we talk about the force on that one object, or maybe the momentum on maximum 2 objects. But fluids are really, again, if we zoom in, a collection of trillions and trillions of little particles that what's happening fundamentally? They're bumping into each other. So sometimes that's helpful to keep in the back of your mind, okay? So what causes a fluid to flow? Before it was always stagnant, but what might make a liquid, say, flow? Okay, I'm probably going to use the word water a lot, even though this is all applicable to all fluids, but water is the most common that we're going to see. Here I have a pipe, thanks to F.5 for making this animation. Here I have a pipe that's totally filled with water, and the water is not standing still. Maybe like the little dots represent water molecules, or I can press this button that shows just a few more dots. The water here is moving to the right. Okay, something must have caused that water to accelerate if it was standing still initially and then move to the right, okay? So what is going to cause that fluid to flow? I give you the punchline right here. Pressure. Pressure is kind of the replacement. It doesn't have to be officially, but it's kind of been acting as our replacement for force, okay? Pressure is equal to force over area. We learned about that before, okay? We use pressure more because remember, zooming into all these billions upon billions of particles, the particles are able to slam into each other in all the different directions. It's not just accurate to say there's a single direction. Okay, but if I want pressure, if I want a fluid to flow, I need an overall pressure, say, going to the right, which means really it's a callback to Newton's second law. If this water was stagnant, if it wasn't moving, but I want it to accelerate, what did we learn? Sorry, that's a sloppy sigma. If I want something to accelerate, I need a total force, okay? Now, a total force when it comes to pressure, that means for a given cross-sectional area, and sorry, I'm not going to draw this well, but this is a pipe here, so there is some cross-sectional area. This diagram has a better job showing the cross-sectional area. So here's some cross-sectional area. There must be some overall force on this side that's overall applying some pressure. If I had equal pressures on both sides, that would be like having equal forces. Well, the pressure would cancel out and the fluid wouldn't flow. So a fluid will flow when there's an unbalanced pressure, when there's some unbalanced force in a given area that's acting on it, okay? Okay, so now we have the basics of what causes a fluid to flow. We're going to see in a few videos different ways to analyze and to see this motion, okay? We're going to start with the first equation, analyzing how fluid flows. Now, first thing, when we're talking about a moving fluid, we're going to make some simplifications, okay? Remember, this AP Physics 1 class does not rely on calculus, okay? So we're going to use tools and use simplified versions of scenarios that we can use our algebra to approach things. There's kind of 2 different categories fluids can flow, or liquids, say water can flow. Maybe you've heard of turbulence before. Maybe you've even heard of words like eddy currents, okay? That's when there are disruptions in how a liquid or gas is flowing through a material. Very interesting physics, but we're going to focus on the more simplified laminar flow. The AP exam is never going to question you directly, what does laminar mean? But it means when the fluid is flowing kind of nicely in the same direction, there are no obstacles in the way, okay? So that's one of our assumptions. We're just going to deal with fluid that's always flowing in the same direction. It's moving together, I should say. Okay. Also, we're going to assume for this little math proof that we're about to write down that the pipe is totally filled. We don't have a water hose where there's just a trickle of water. Imagine the water pressure, the fluid, is enough so that it's filling the whole container. The first equation about moving liquid has to do with how much liquid or how much fluid is flowing. It's called the mass flow rate. It's pretty simple if you think about it. It just has to do with how much mass, how much water is flowing in a given chunk of time. You normally don't think of chunking water into pieces because it just seems like one thing, just water. But imagine I have a hose and I kind of zoomed in. Imagine I could freeze time. We could look at one chunk of water at a given time. That chunk of water has mass, and the amount of time it takes to, say, flow a certain distance, that's the mass flow rate, how much water is moving through the pipe, okay? Now, this is not written classically as m over t. Let's remember that we learned the equation for density. Density is like how jam-packed the particles are in a given material. Density is mass divided by volume. So that means the mass of a substance is based on the density times the volume, how dense the liquid is or the gas, and how much volume it's taking up. So instead of mass, I'm going to write density times volume divided by T. This V here is this V right here, the volume of my chunk of water. I can go one more step, okay? Volume for any object, okay, any shape, it's some version of base times height. This looks like a cylinder of water. I have a cross-sectional area here, and this cylinder has some height or some width. The total volume, it turns out, I'm going to keep my density. It's based on this cross-sectional area times this distance. That's how I get the volume. A times D, that's representing the volume. And then one more step, team. Oh, man. Distance divided by time. Remember, this is a stagnant image, but if I pull up my animation again, this fluid, this water is flowing. It's traveling some distance in a given time. So if I'm traveling a distance, this width in a certain amount of time, that's speed. That's average velocity. So that means my mass flow rate is density times A, the cross-sectional area, times the velocity. Careful, this V here is not the same as this V here. I'm so very sorry. The big V, that's representing the volume, but little v, this is cross-sectional area. I'm sorry, little v is the speed. Oh man, I'm messing myself up. So you should write this equation down. If you're taking notes, I got density right here. I have the cross-sectional area of, say, the pipe. And this is the speed the water is flowing through the pipe, okay? That's how we figure out the mass flow rate, how much mass is flowing, okay? Last key idea, okay? Letter D, this is my last topic. It's really an application of this equation. There's something known as the continuity equation, and I have almost a question for you. It says, imagine we have fluid flowing through a pipe. But the pipe's diameter, it gets smaller. That's what this diagram says, okay? It says I have water, it's flowing to the right, just like the animation that I showed you, but the diameter, it gets more narrow. What do you think is happening to the speed of the liquid when it narrows, when it gets to a narrower chunk of the pipe, okay? It turns out, team, we're going to use this mass flow rate to prove our equation. I'm going to break this up into two pieces. There's two sections. There's section of pipe kind of 1, this section here, and there's section of pipe 2. Okay, in section 1, maybe I'll do two different colors. For section 1, the amount of water that's flowing, that's given by our flow rate. That's based on the density of this water times the area of this pipe. This pipe has an area of A1, that's how they labeled it. The speed of the water is given by this V1. And then over here on the right-hand side, I'm going to switch to yellow. Okay, over here, the same mass flow rate. It's the same density. It's still water, so it's going to be the same density regardless. But the area here is A2, and then the speed is V2. Now, the core thing to use this equation or to answer this question is how do these things compare? And this is actually going to rely on some inherent knowledge we need about mass, about matter. Team, your table that maybe you're sitting at never mysteriously vanishes. It turns out that on our scale, and even at the atomic and molecular level, matter never just disappears. Matter doesn't randomly conjure itself into existence, and likewise, matter does not disappear. I can move a table. Heck, I could have a chemical reaction and rearrange atoms and molecules, but atoms and molecules, those particles, do not disappear and reappear. It's something known as conservation of matter, okay? So as this liquid is flowing down this pipe, well, I can't have any water just magically reappear appear out of nowhere or just vanish out of thin air, okay? That would create all kinds of problems. So all of this matter has to be staying the same. So with that in mind, the core idea, team, is that the amount of matter that is flowing in a pipe, it stays constant in total. Whatever the amount of mass that's flowing in this section has to equal the amount of mass that's flowing in this section. And so with that in mind, let's solve this equation for V2, okay? Now, it's the same density, it's still water, so I can cross those two things out. If I solve this for the volume here, V2, well, that's equal to the cross-sectional area A1 times V1, the speed of the water here, and I'm going to divide by A2. So here's my equation. Sorry, I have some slanted handwriting going right here. Team, notice A1 is bigger than A2. So if I was to highlight this section, this fraction is bigger than 1. So that means V2 is equal to V1 multiplied by some number larger than 1. Simply put, V2 is going to be greater than V1. Let me show you that diagram again. Now it's a little reverse this time, but let's hit play and see what happens. Here, the water is slowing. Notice this is not the same example as my other picture. Team, I can't have water mysteriously vanish, okay? However much water is entering this pipe has to leave this pipe. Otherwise, we're assuming like the pipe isn't going to burst. Remember, it's staying nice and full. No atoms can be vanishing. If atoms just disappeared, then we'd have like weird vacuums occurring. And I can't be adding magically particles. That wouldn't make any sense. So however much water is being added on this side has to leave on this side. And because if we imagine kind of this cross-sectional area, there's more water over here in this given volume, it must be moving slower in this animation, okay? Or the opposite case, here the water must be moving faster. I've reset my animation to more accurately match this diagram here. Again, however much water is entering in this section has to equal the amount of water that's leaving. I can't have any water magically appearing or disappearing. So since I have so much space for water over here compared to here, I have a much smaller nozzle. The water has to speed up. So this equation, this thing known as the equation of continuity, it's used to describe how the speed of a fluid is going to change based on how the diameter of the pipe is changing. For a given fluid in a pipe, decreasing the cross-sectional area is going to increase the speed of the fluid. This is an equation on the AP equation sheet. Here it is. Now notice, there's no density in this equation. We had density in this original equation for mass flow rate, but 99 out of 100 times, we're dealing with the same liquid flowing through a pipe. So if it's the same liquid, it's the same fluid, it's the same density, so that cancels out. But here is our relation. How fast the liquid or the fluid is flowing, it's based on the diameter, it's based on the cross-sectional area of a given pipe. We're going to do some practice math calculations with this in class. And then again, this is on the AP exam. You may be asked to analyze or calculate based on this equation and this idea. Okay? That's all for this video. We'll see some more examples and some more equations studying moving fluids in the next videos. Thanks a lot. Bye.